Didn't say a whole lot about fine-tuning, but did say one thing. The fine-tuning argument, we all agree, and when he says we, he means his people. People that believe the same way he does. Is the most intriguing. It is not trivial. We all say that. We all agree about that. So he is saying that he's not saying, oh, it's fine-tuned. He's just saying we know that this argument is a very strong argument, and we need to deal with it. And finally, the king of atheism, Richard Dawkins, British evolutionary biologist and writer. He is an emeritus fellow at the New College, Oxford. Dawkins is a noted atheist and part patron of the British Humanist Association and a supporter of the Brights movement, naturalism, and is well known for his criticism of creationism and intelligent design. Last time we had a group meeting, we talked about naturalism. And naturalism and materialism, the same thing. Everything comes from matter and energy and the laws that control it. There's no other things in the universe. Quote, physicists have calculated that if the laws and the constants of physics had been even slightly different, the universe would have developed in such a way that life would have been impossible. Of course, he's not a physicist. He's an evolutionary biologist. So he's given them their due. He said physicists have calculated. Of course, all those guys we just talked with that were here on the screen, they were physicists or astrophysicists, something like that. Let's talk about the nitty-gritty. Now we brought science in to give their presentation. So here's what science says. Science says there are 4 forces of nature. 1, strong nuclear force. 2, the weak nuclear force. 3, electromagnetic force. And 4, force of gravity. All forces in nature fall into one of those categories. The first 2, I would tell you, are just acting within the nucleus of an atom. So we don't have a whole lot of experience personally with those 2 forces. But without those forces being what they are, we wouldn't be here. Nothing would be here. Electromagnetic force, well, that's the force of, well, we know about electricity, the force and the energy we get from electricity, but electromagnetic force is just how your molecules are aligned in a piece of material that could be magnetic, like, you know, iron can be magnetic, steel. There's a magnetic core in the world that protects us, keeps all kinds of stuff from hitting our planet. A strong nuclear force is a strong attractive force between protons and neutrons in the atomic nucleus that holds the nucleus together. This force increases when the distance between protons and neutrons increases. This force is only effective within the nucleus of the atom. You know, gravity is stronger when you're closer to the item, okay? What you weigh on this Earth is actually the gravity between your mass and the mass of the Earth. And the mass of the Earth, the center of the mass of the Earth is 4,000 miles. So I weigh like 150 pounds. What? What? So that means the force of attraction between me and the Earth is 150 pounds of force, or maybe a little more. That was in 8th grade, I'm sorry. But if you think about that force, it's like trying to pull something apart that's attached with a real strong rubber band. Okay? At first, when they're close together, the force isn't much great, but when you start trying to pull them apart, that force gets greater. If it wasn't there, protons are both positively charged. They would repel each other, and they do repel each other. But there is a force that holds them together in the nucleus. That's hard to understand. It's there. They measured it. So there you go. That's what that is. Strong nuclear force. If the force was 5% greater or 5% less, life would be impossible in the universe. If it was greater, no hydrogen would form. Atomic nuclei for most essential elements would be unstable, no life chemistry. If less, no elements heavier than hydrogen would form no life chemistry. You know, 5% is probably a lot less than that, but that's what the literature said. But just think about that. Who decided, or what decided, or how it was decided that that force would be what it is? The value of it. Okay, you understand what I mean? Okay. If the value was a little less, a little greater, nothing would work. It's like Goldilocks. Dad, you're too hot. Mom was too cold, but baby parents are just right. So everything's just right for that to work. The weak nuclear force is really like back decay, in other words, radiation. The weak interaction of weak nuclear force is responsible for some nuclear phenomena such as beta decay. It would be very, very hard and long to explain why we have to have a weak nuclear force, and we're not going to take the time to do that. But, wait a minute, back up. Okay, I think, you know what? I am missing a slide. I apologize for that. It just says that the weak nuclear force was just a little bit less, a little bit greater. Again, we couldn't live in this earth or in the world of the universe. All right, force of gravity. That formula, and I'll explain that, the force due to gravity is equal to G, and that G is a number, pure number. Well, it's got units to it, times the mass times the mass. In other words, my mass times the mass of the Earth divided by the radius squared. The distance between the center of gravity of me and the Earth, like I said, was 4,000 miles. The G is the fudge factor. Know what I mean by that? It means that nobody knew what G was until they started realizing what gravity was, and they started calculating it. And Newton started that. Now, some of you will say, well, Newtonian physics has gone out the door. We have quantum physics. There are differences, I agree. But the initial formulas were true. We actually, most of our space program was based on that formula right there. G is a very small number. Gravity is a very weak force. Okay? Because that R squared in the denominator makes it very small when you start getting further and further and further away. But nobody can tell you what G is. Why G is what it is. It is, but if we didn't have it where it is, we wouldn't live here. We wouldn't live anywhere. Nobody would. If greater stars would be too hot and burn too rapidly and too unevenly for life chemistry, if less stars would be too cool to ignite nuclear fusion, many of the elements needed for life chemistry would never form. For you, nuclear fusion, for some of you, if you don't know what that is what makes the sun hot. That's what makes the sun glow. That's why we can live here. Okay? Nuclear fusion is basically hydrogen, which is the basic element in chemistry, combining two hydrogens together to make helium. When that happens, it gives off a huge amount of energy in the form of light and heat. So that's what has to be happening for us to live. If that G was a little different, I've heard 1/10 of 1/100th of a percent, it wouldn't work.